Hello and welcome to the webinar, Saltwater Pool Troubleshooting Beyond the Equipment with Alicia Stevens. She's Director of Education from BioLab. We're gathering in the last few attendees, so bear with us for a few more seconds and then we'll start actually right now because we always start right on time and it is the very top of the hour. So let me just say again, we have Alicia Stevens, Director of Education at BioLab. She's here to talk to us about saltwater pool troubleshooting beyond the equipment. My name is Scott Webb. I'm editor of Aqua Magazine. I've been in this position for a little more than 20 years, and that whole time I've been watching Alicia give great seminars and education. She's truly an icon of education in this industry, and we're very fortunate to have her today. So there's a lot to cover. It's a great topic. Let's get started.
Thanks, Scott. I appreciate it. I'm always happy to be here with Aqua and ready to talk about chemistry in any form, but today we're just going to talk about saltwater pools. I'm excited about that. So I want to jump right in. We're going to start with just kind of the basics of saltwater pools, but as we kind of weave through this, I want to be clear that what we're tackling here is chemistry. We're not talking about the cell or troubleshooting actual cells. There's so many different kinds and shapes and sizes out there. What I'm focused in on is the actual chemistry of the water and some of the challenges that come with saltwater pools and some of the best ways to manage that. So yeah, we're gonna jump right in. If you have questions or anything, feel free to drop them in the chat. I know that Scott's gonna keep an eye on that for me and let me know as they come up, or we'll take them at the end depending on what's coming through. So please don't be shy. Ask your questions as we go. I'm happy to take as many of them as we have time for as we move through it. But anyway, thank you for the introduction, Scott. I am Alicia Stevens, Director of Education for BioLab. I've been with BioLab for about 24 years now, so I'm nearing the quarter century mark in the industry. And I love to talk about chemistry. So today we're just going to talk about saltwater pool chemistry, which I think we can all agree saltwater pools are extraordinarily popular in the swimming pool industry, and they're not dropping off. They're not getting less popular as time goes on. I think more and more pools are being built with salt generators on them. More and more people are converting over to salt. We're starting to see salt coming into our spas and impacting spa chemistry. So it's certainly a trend in the industry that's here to stay. And it's good chemistry. It's a great way to take care of a pool. And it's certainly a good way to make pool care easier if you do things right. So I'm going to focus in on maybe some of the challenges that come with it and how to make sure we're doing it correctly so that those pools are well balanced and clean and clear and safe to swim in. So with that, I always like to start with a reminder, saltwater pools are still chlorine pools. We're simply taking a salt molecule, which is Na and Cl being the chlorine, and through the process of passing it through our salt cell, we break apart that molecule and we turn that chlorine molecule into hypochlorous acid, which is our killing form of chlorine. The beauty of this is you don't have to handle active chlorine. You don't have to put it in the pool where it smells or spills or anything like that. You don't have to transport oxidizers or anything along those lines. It's an automated system to be able to sanitize your pool. I always say a salt cell is like a little chlorine manufacturing plant right there in your plumbing. So you're actually manufacturing your active chlorine on site. So I always want to start here just to make the point that, again, saltwater pools create hypochlorous acid. It's the same active killing ingredient that you get from every other type of chlorine sanitizer that we use in the pool industry, whether it be trichlor or dichlor or cal-hypo or lithium if it was still around. I think we all missed that a little bit. Sodium hypochlorite, if any of you are using chlorine gas in the commercial setting. All of those things are very different ways to add the chlorine molecule to the pool, but ultimately, at the end result, every single one of them creates hypochlorous acid, and that again is the killing form of chlorine. So that's what's going to go out and kill the bacteria, do the sanitizing, oxidizing, all those things that we need chlorine to do. So salt's no different. It's putting in a salt molecule, but just like trichlor, dichlor, cal-hypo, or any of the others, it's going to create that hypochlorous acid molecule that's going to do all the work in the pool. So what I want to focus on is some of the issues that come along with saltwater pools, because there's kind of a mentality with consumers more than anything. I know as pool professionals that we're not guilty of this, but there's a mentality among consumers and pool owners that all you have to do to take care of a salt pool is add salt. And that's not the truth for how to properly maintain a saltwater pool. Yes, adding salt is an element of it, but in reality, your salt cell is replacing basically one part of your pool maintenance routine, and that's sanitizing. That's what it's doing. It's creating the sanitizer. So that's one element that we have automated, and we've made it super easy to do, and we've made it so we don't have to transport those toxic chemicals and things like that. But ultimately, there's a lot of other things in the chemistry of saltwater pools that we need to be aware of and that we need to manage as part of the process, because we want that pool to stay clean, we want it to stay clear, and we want to make sure that salt cell, which is not an inexpensive investment, we want to make sure that cell lasts as long as possible, and chemistry is the key to all of that. So we're going to dig into some of the things you need to be aware of with saltwater pools. These are the most common issues that you run into. pH balance, we're going to tackle that first. We'll talk about not being able to hold chlorine and some of the root causes of that. We're going to talk about combined chlorine and what the right way to handle that is and why it builds up so quickly sometimes in saltwater pools. And then we'll at the very end just talk a little bit about cloudy water and some of the things that you need to be aware of in salt pools when your water starts to go cloudy. So I want to start with just a quick recap or refresh of why water balance in general is important. And specifically, why is pH so important? So pH is an issue in saltwater pools simply due to the nature of how we break apart the salt molecule and turn it into active chlorine. I'm going to show you an equation here in a minute that explains that. But ultimately, keeping pH in balance is a very important part of pool care. And if we went with the just add salt mentality, sometimes that comes along with saltwater pools, we would find that pH is constantly too high in the water. And with that, we get corrosion. Well, not a lot of corrosion. We get more scaling. We get damage to our surfaces. Swimmers get uncomfortable. They get itchy in the pool. And one thing that we forget about is the fact that pH has a huge impact on how well your sanitizer that you're busy making from your salt cell, that active sanitizer that we're making and relying on to do the work, is dependent on pH to be effective and efficient. So when pH gets out of balance, that sanitizer isn't as effective. When it's not as effective, then we probably have to dial our salt cell up a little bit to try and compensate. And then there's this domino effect of what happens simply because that pH is constantly drifting up. And if you're not managing that, it leads to additional problems. So this just shows your pH schedule or pH scale. It's a 14-point scale. Towards the 0 side of the scale, it's very acidic. It means we have a lot of hydrogen ions in the water. And then on the opposite side of the scale, it's very basic, meaning we have a lot of hydroxide ions in the water. Ultimately, we want to be fairly neutral, a little on the high side of neutral, between 7.4 and 7.6. That's the ideal pH range. And that's ideal for a couple of reasons. One, the pH of the human eye is 7.5. So if your pH is balanced in that ideal range, the kids can swim around, they can dive for all those things they dive for. They don't put their goggles on. You know, sometimes kids get out of the pool and they look at you and their eyes are bloodshot and swollen, and you're like, whoa, what happened to you? And they're like, I had such a great day, and they're rubbing their eyes and all that stuff. And we tend to blame that on chlorine most of the time. But ultimately, pH is the culprit. When pH is out of balance, it irritates the lining of your eye. And then that's when you get bloodshot eyes that sting or itch or anything like that. So it's important for comfort, but it's also extraordinarily important, like I said, on how well your chlorine is able to work. So as your pH goes high, which is what happens in saltwater pools, as that pH goes up, chlorine gets less and less and less effective as it goes. So we need it to be hypochlorous acid in order to be able to kill and sanitize and do all the work we need it to do. But as the pH goes higher and higher and higher, that hydrogen ion falls off of the hypochlorous acid, leaving behind a hypochlorite ion that doesn't do anything for you. So it's still chlorine, it's still in there, and you can attach the hydrogen back onto it and make it active. But ultimately, when that hydrogen ion is off and it's OCl, then your chlorine is not effective or efficient. So the higher your pH goes, the more chlorine that gets, as I call it, it lays around on the couch watching Oprah all day instead of going out and doing the job that it's supposed to do. So then you would have to compensate by creating even more chlorine to try and overcome that. So for example, at a pH of 7.5, chlorine is 50% active, 50% not active. That's a great balance. That means you've got chlorine working and you've got chlorine still kind of waiting to be activated, so you don't use everything up at once. As your chlorine level goes up, say to 8.0, which I see in saltwater pools all the time, at a chlorine or a pH level of 8.0, your chlorine is only about 75, 70, or 25, 24% active. 75, 76% of it is lazy. So you're only using 1/4 of the chlorine that you're making. As you get up even higher, if you get to a pH of 8.5, which again I've seen in saltwater pools, then your chlorine is about 9% active, and 91% of it is in that inactive form. So even if you're pumping out 10 parts per million of chlorine into the pool, which that would be tough for a cell anyway, you're only able to utilize 0.9 parts per million of it at that point. So that pH has a huge impact, and as it goes higher and higher, your chlorine gets less and less efficient. As it gets less efficient, you need to make more and more of it to try and compensate. So focusing in on balancing pH is an important part of maintaining a saltwater pool. So everything that comes into a pool will cause your pH to change, but ultimately the reactions that occur when you are creating active chlorine from salt very, very quickly cause pH to change. So I want to illustrate that very quickly. So you have, now all of you that stopped listening because I put a chemical equation up, come back. This is not hard to look at. I promise it'll be quick and easy, but I want to show you what really happens when you put a salt molecule into the pool. So you have water, right? Obviously water in the pool, and you add salt to it. You add the little lightning bolt is the electric charge that you get when the salt passes through the actual cell. And when you pass that through the cell, you actually break apart the salt molecule, and for a minute, you create chlorine gas. So Cl2 is chlorine gas. You've created chlorine gas at that moment. It's still reacting in the water, but you've got chlorine gas, you've got hydrogen, and you've got these two hydroxide molecules, which are what get left over after the sodium chloride molecule, the salt molecule, breaks apart in the water. So you've created chlorine gas, that's great, hydrogen, fine, but then you've got these two hydroxide molecules that are also left behind. The chlorine gas keeps reacting in the water, and ultimately it combines and forms HOCl, which is our active form of chlorine, right? So we've broken apart the salt cell. We've created temporarily a chlorine gas. That chlorine gas then recombines in the water, creates hypochlorous acid, which is great. It leaves behind a hydrochloric acid molecule, which is good. This is low pH, hydrochloric acid. Sodium hydroxide is high pH. So you would think, well, you've got low pH and you've got high pH. Those two things would balance each other out, and the pH should be fairly stable. But the problem is, in this first step up here, we have two sodium hydroxide molecules, and we only create one hydrochloric acid molecule. So when the equation is all said and done, and we've recombined everything into what it's going to be, and we've created our active chlorine, which is great, we have left behind that hasn't been neutralized or offset one sodium hydroxide molecule. And that is a high pH molecule. So for every salt molecule we break apart, we leave behind a high pH molecule in the water, which is why pH constantly goes up in a salt pool, because ultimately every time we break apart that molecule, that's what we're leaving behind. So I get asked a lot of the time, well, how do I keep that from happening? You can't keep it from happening in a saltwater pool. It's just part of the actual process of creating active chlorine out of salt. So you can't stop it from happening. You can manage it, you can offset it, you can balance it, Again, it's more than just adding salt, but you can't keep it from occurring. So part of saltwater pool maintenance is constantly bringing that chlorine back down to where it's supposed to be to ensure that swimmers are comfortable and to ensure that ultimately your chlorine that you're making and relying on to do the work is able to work effectively and efficiently. So here's some of the properties when pH gets out of balance. We don't worry in saltwater pools about acidic water much, unless you just overdo it on your pH adjustment. Acidic water is corrosive. It's very hard on surfaces. It causes wrinkling of liners. But basic water is what we usually end up with. Basic water turns cloudy very easily. Calcium becomes less soluble. We're going to talk about that. So that leads to scaling. Your chlorine, as I talked about, gets lazy. And again, your eyes and skin get itchy. A lot of people get out of a pool and they say, oh, I'm itchy. That's just pools. You should never be itchy when you get out of a pool. If you are, there's something wrong in the water balance. It's not the chlorine. It's probably the pH being out of balance and causing your skin and your eyes to have a reaction to it. So always, if a bather ever says they're uncomfortable for any reason, always look at your water balance, because normally there's a parameter, usually pH, that's out of place. So for saltwater pools, adjusting pH becomes really a weekly job. So if anybody is doing service on saltwater pools, you should always be prepared as part of your service call to put in either sodium bisulfate or muriatic acid, whatever your preference is. Some people like dry acid, some people like muriatic acid. It doesn't matter. They're both very effective, but ultimately you've got to be prepared to add an acid. You're adding more hydrogen ions to bring that pH back down to the manageable level where your chlorine is good, it's efficient, your bathers are comfortable, and everything's operating the way it should be. If you let pH go and you don't adjust it at all, it's just going to continue to get higher and higher and higher. And then I start to get calls of people saying, I've got 10 parts per million of chlorine in my pool and it's turning green. How is that possible? Well, my first question for that is always going to be, what is your pH? Because at those higher level pHs, that's 10 parts per million of chlorine is not all active, and there's very little of it actually active and doing the job that it's supposed to do. So that's one of the biggest problems that we find in saltwater pools, that maybe not a problem, biggest challenges we find in saltwater pools that we have to manage and make sure that we adjust for, so that again, the water can stay clean and clear and comfortable for swimming. The second big issue that we find, and it's probably, besides pH just happening regardless of anything else, it's probably the most common problem in saltwater pools, and it can be a little bit confusing, and that's not being able to hold a chlorine residual. And that's tough for saltwater pools, because a lot of times the gut instinct of whoever's taking care of the pool, especially if it's someone that's residential, maybe trying to do it themselves, it's just add more salt, right? That's kind of what they've been taught. The pool's cloudy, add more salt. I can't get any chlorine, add more salt. My kid's failing math, add more salt. Adding salt will solve all of your problems, when in reality, adding salt or low salt levels, well, it can be one of the issues that leads to not being able to hold chlorine. It's actually not very common at all. That is the issue. Once salt is in, it doesn't really go anywhere very fast. So if you've established your salt residual at the beginning of the season, and you know that you had plenty of salt in there, it doesn't just disappear. So adding more salt is usually not the issue. When you start saying, I can't hold free chlorine in the water, it's one of two root causes. Number one, you're making plenty of chlorine, but it's being consumed by contaminants in the pool water. That's what we call chlorine demand. We're going to talk about that in just a second. Number two, the cell itself is unable to produce enough chlorine to keep up with your regular bather demand that happens in your pool. So it's going to be one of those. You're either making plenty of it, but you've got so much garbage in the pool that you can't keep up with it, or you're just not making enough in the first place. So first question I always ask when someone says, I cannot maintain a chlorine residual in my pool is your chlorine stabilized? And that's an important question, simply because when you're making chlorine from a salt cell, you're creating unstabilized chlorine. That means the sun will burn it up very quickly. That means you lose half of everything you make every 35 minutes in your pool. So if you make, just for generalities, 2 parts per million of chlorine every half an hour, you're going to lose half of that to the sun, just wasted away, burnt up by the UV. So you're going to have a really hard time if you're only keeping half of what you make. You're going to have a really hard time having enough chlorine to keep up with the demand that you have in the water. So stabilizers are important. That 35 minutes becomes 6 hours once you stabilize the chlorine. So instead of losing half your chlorine every 35 minutes, now you lose half your chlorine every 6 hours. So chlorine has a much longer span of time to do what it's supposed to do, which is kill bacteria, oxidize, kill algae, do all those things that chlorine does, without just being burnt away uselessly by the UV light of the sun. So make sure that you are establishing a stabilizer residual. We always recommend between 50 and 60 parts per million for saltwater pools. Good rule of thumb is 10 parts per million of stabilizer will protect 1 part per million of chlorine very effectively. So you want to protect all that chlorine that you're making and spitting out of that cell. You want to protect all of it, because the more of it you're able to protect, the less of it you have to make. And the less of it you have to make means your cell can be dialed down further, meaning it runs less, meaning it lasts longer, and ultimately the customer is happier because they're replacing it less often. So that's always the first question. Just a quick option here, we do offer a liquid stabilizer. I always say if anyone has ever put granular stabilizer in a pool, it's slower than my grandma, and she's not alive anymore, because it is absolutely a difficult product to get in. So you can put it in with a granular. There are liquid options out there that go in immediately. Obviously, ours happens to be the natural chemistry instant conditioner, but ultimately the key is getting the stabilizer in the water so that you are protecting what you're making. Because if you're not, your cell's just making chlorine that is burning up without ever having a chance to do the job that you need it to do. All right, so back to root cause. First reason why you wouldn't hold chlorine in a saltwater pool is chlorine demand. And that's simply you have too much garbage in the water. And so all the chlorine that you're making is getting burnt up very quickly. And a lot of times, the symptom of that is you have no free chlorine residual. A lot of times what people assume is when they stop holding chlorine in a saltwater pool, their first assumption is the cell stopped working. And ultimately, that is possible for sure. And we'll talk about some of those reasons why the cell's not functioning the way it should, but it's not always the issue. A great way to test if your cell's working is simply take a water sample right from your return jet and test it for chlorine. If it has chlorine in it, then your cell is generating chlorine, and you can tell that you're actually creating it. If you take it directly from the return and you don't have a chlorine residual in it, then you know that there's a problem with the cell itself. So that's a great way to determine, where is the problem? Is it in the pool or is it in the equipment? And you can start to dial it down at that point to determine what the actual issue is. But chlorine demand is very common. It's common in salt pools, it's common in traditional chlorine pools, it's common in every pool. And unfortunately, as a human race, we're not very kind to our environment. And the worse we are to our environment, the more things come into our pools from a lot of different sources. Pollution, rain, fertilizers, source water, all these things get into the water. And if chlorine will interact with them, then they will eat up chlorine. So the more things that chlorine has to interact with, the more chlorine it takes to be able to keep that residual where it's supposed to be. So I always use analogies when I teach, and the analogy I use for chlorine demand is, I think we've probably all at one point or another in our lives, we've overdrawn our checking account, right? And if you overdraw your checking account by $100 and you put $50 in the bank, do you have any money? No, you don't have any money, right? Because you're overdrawn. But you did make the problem better. You're closer to having money. You're out $50, but you're closer to having money. So ultimately, you've made the problem better, but you haven't solved it yet. You put another $50 in the bank. Do you have any money? Not yet. You're out $100, but your bank account still reads zero, but you've made the problem a lot better. You're solving the issue or the overdraw. You put a third $50 in, and now you've got $50 because you overcame that deficit that you had in your bank account. Chlorine demand's the same way. You get this overdraw, this buildup of garbage, dirt, debris, bather waste, all sorts of things like that. And your chlorine is working really hard and it is breaking it down, but it can't get back to zero until it gets rid of all that stuff that gets built up in the water. A salt cell can only make chlorine so quickly. So when you get that big overload sometimes and you're trying to rely on the cell itself to produce enough chlorine to overcome all of that, it can be a very slow process, especially if the chlorine demand is caused by organics, which most of the time, quite honestly, a very big part of chlorine demand is organics. Organics are slow to oxidize. These are bather waste, body oils, urine, sweat, fecal matter, personal care products, pharmaceutical products, which come out of your sweat and in your urine. All of these things eat up a ton of chlorine. So if you had a pool party with 10 little leaguers in the water and they drank 85 juice boxes and your bathroom floor never got wet, it's very, very likely that you overdrew your checking account and you have a chlorine demand that you need to break. Again, the cell's going to have a hard time generating chlorine fast enough to take care of that very quickly. Also, just a point I always like to make is if you say that doesn't happen to me, I only have adults swimming in my pool, adults pee in pools too. They may tell you they don't, but they're lying to you. I always say you ask 100 adults if they pee in pools, 10 of them say yes, and 90 of them lie to your face. So just be aware of that bather waste comes from all shapes and sizes, and ultimately pool parties are one of the biggest causes of chlorine demand that we have. So if you find yourself in a position where you have a chlorine demand, you've got some options to get rid of it. Your cell is probably not going to be able to do it. It just can't generate enough chlorine all at once. So you can add chlorine, right? There's nothing wrong with shocking saltwater pools independently of the cell. It does not hurt anything. It does not cause a problem. You can add shock products to that pool in order to help overcome the problem. Option two, you can use products like flock products, clarifiers, phosphate removers, anything that will physically take out debris. And then ultimately, you're still going to have to add chlorine, but you'll probably end up adding less chlorine to the water. Or you can do a partial drain and refill. You can always physically remove whatever's in the water, put some fresh water in that doesn't have a demand, and then ultimately you use less chlorine to reestablish your residual. So you have options. These are some of the products that can help. Phosphorus is going to take out phosphates, which will help reduce algae's ability to grow and reproduce, which will eat up less chlorine. Clarifiers will help bond together debris, dirt and debris that chlorine might otherwise have to break down and take it out through your filter. Something like Pool First Aid, which is a high-level clarifier and an enzyme product mixed together. Enzymes will help digest some of the stuff that chlorine would otherwise have to eat up, and then the clarifier will help remove some of the other debris that gets left behind. So these are the types of products that can help in a saltwater pool so that your cell itself has a chance to catch up and be able to produce enough chlorine and establish a residual. So that's usually what's happening. It's usually not that the cell just magically stopped working, but it's usually just the fact that you've got a buildup of debris or dirt and you need to be able to overcome that. Again, it's okay to shock a saltwater pool. You're not going to hurt it if you shock with cal hypo or dichlor or trichlor or any of the shock liquid chlorine. It doesn't matter. It's okay to shock a saltwater pool. Now, if we switch to kind of the second root cause of not being able to hold chlorine, it is that the cell cannot keep up. It cannot make enough chlorine to be able to keep up with even regular demand, let alone chlorine demand. And that comes from a lot of different places with the cell. It could be that it's not running long enough, it's not the right size. We're going to talk about each one of these. It's scaled up. There are some water balance attributes that can lead to that, or the cell itself is just old and it's not able to function anymore. So these are all the things that you need to look at. Again, if you put that water bottle up to the return jet and you're not getting a chlorine residual, you know the cell's not getting the job done, that's when you look at these types of things. First and foremost, look at your cell runtime. The cell only generates chlorine when the pump is turned on. So if the pump and filter are on a timer, that means your salt cell is on a timer. make sure that that timer is set long enough that your cell is able to run long enough to be able to keep up with what you need to do for manufacturing the chlorine, right? The other thing I always want to caution you with is with the popularity of variable speed pumps, a lot of people like to run their variable speed pumps for lots and lots of hours on very low speeds. That's great for energy and terrible for chemistry. So you have to make sure that on those variable speed pumps, they're good. I have nothing against variable speed pumps. They are really good and energy efficient, but you can't just leave them on the low setting and say, I run my pump 24 hours a day. You've got to bump them up to the high setting. You've got to get them up where you're turning the pool over every 6 to 8 hours and run that for 10 to 12 hours a day at a minimum to make sure that you're moving enough water through the system. Because if you're not moving water through the cell, you can't create chlorine from the salt that's in it. And if you don't move enough water through the cell, you're not creating enough chlorine to take care of the actual demand in the pool. You can always adjust cell runtime. You know, most cells run as a percentage. So for 100-minute cycles, if you set it at 50%, it would run 50 minutes out of 100. If you set it 20%, it would run 20 minutes out of 100. Obviously, the higher the setting, the more time it spends generating chlorine. But again, only generates chlorine if the pump is running, and only generates chlorine in the water that's able to pass through it.
Alicia, I just had a quick question. I also wanted to grab, we've been getting some great questions. I just kind of wanted to maybe deal with one or two and to tell everyone that's out there that we'll actually have some time at the end to go over questions. When you were mentioning the variable speed pumps on low, will your cell continue to function even at like a very low RPM setting? And are there other issues with chemistry that you mentioned that's not really the best thing for pool chemistry? Can you just elaborate on that just a little bit?
Yeah, a couple of things. One, most salt cells have a flow switch on them that requires a certain amount of flow for them to function. So if your variable speed pump is set too low, and I don't know the numbers, I'm just being honest. I don't know, you know, and they kind of vary from pump to pump. But if it's set too low, you're not moving enough water through, you're not going to generate. You'll get a flow light or a flow warning usually on your system. So you may not be able to generate at all. And if it's set too low, you have to move water through in order to be able to generate the chlorine, and you're just not moving enough water through. The other thing with variable speed pumps in general is, again, if you're not moving water through the system, you're not filtering it either. And filtering is a huge element to properly taking care of any pool, including saltwater pools. So the lower you run it, the less turnover you have, which means less water moves through the filter, less water moves through a heater if you have it, less water moves through an ozonator or an ionizer or the salt cell or your chlorinator, anything that you're using to put sanitizer or to help with your water chemistry. If the pump is not moving enough water through to effectively do that, you're really struggling then to keep up with what you're trying to do. You rely on the movement of water to disperse chemicals, whatever those chemicals happen to be. In a salt cell, we rely on movement of water to feed that salt into the cell so that we can break it apart and generate the sanitizer.
And just one quick question, and this is back when we were talking about pH rising. As you use your salt cell, you get the NaOH molecule starting to build up, and you get a higher and higher pH. One of our viewers said frequent applications of low and slow to compensate for the high pH produced by salt systems will frustrate some pool owners. What's a simple way to deal with this and help stabilize the pH in that, you know, as you...
I mean, that's a kind of a tricky question for anybody that doesn't know. Low and slow is a reference to a sodium bisulfate pH reducer product that's part of one of our BioGuard brand. There's not really a great way to do it. There are programs out there. We have a program in our BioGuard brand that's a blended product that is just added immediately, weekly, regardless. It's got some other stuff in it, but pH reducer is one of them. So we created basically a routine for the salt cell owner. So it's not frustrating. You're not constantly measuring and reacting. It's just, you know, you have to put this amount of product in every single week. And that's one of the easiest ways to do it. But like I said, when we were talking about pH, you can't keep it from happening. You can only manage it as it does. So you're either adding pH reducer on a regular basis, which I understand is frustrating to homeowners, but there's no way around that unless you're going to automate it. And you can, I mean, if you're in a commercial situation, you can automate it using an acid feeder or a pump or something along those lines. Those are good options to not have to hand feed it all the time, but ultimately it's just part of the process. So, and it's one of the most frustrating things because people want to say, I did, it's a salt pool, I don't have to do anything to it. And that's just not accurate. You do have to do things to it, and adjusting pH is a constant battle. Now, keeping your alkalinity balanced is great. Adding borates to the water can certainly help. They help buffer pH, so they can help mitigate some of that. But ultimately, you're going to have to add some sort of a pH decreaser, whether it's in a blended weekly product or it's just a test and react based on whatever the test tells you. It's just part of it, unfortunately.
Sure. Okay. Thanks all. We can get going again with the undersized electrolytic cell. I just wanted to grab a couple of those.
Sure, of course. Thank you. So the undersized cell, this isn't as much of an issue anymore, but when we first started out with salt pools, I think everyone was learning. They were, the cell is expensive. It's not an insignificant investment for a pool owner. And a lot of times I think we were trying to minimize costs by selling them the smallest cell possible that we thought might work for the pool. And it led to some issues because small cells struggle to keep up. The smaller the cell is, the higher you have to dial it up. The higher you dial it up, the faster it's going to fail. So we ended up maybe saving money on the front end by putting on a smaller cell, but ultimately we burnt up that cell pretty quickly trying to keep up. So make sure, I would oversize a cell long before I would undersize a cell for a pool, simply because it's going to last longer ultimately. So it's spend your money now or spend your money later. But if you spend your money now, you spend less money later. And that's to me, that's a good way to maintain things. The other issue we find that can keep the cell from being able to properly generate chlorine is scale formation. And this is a huge problem in saltwater cells simply because the environment that we create inside that salt cell is the perfect environment for scale to form. And it's very simple. The higher your pH, the more likely you are to form specifically calcium carbonate-based scale. Calcium carbonate-based scale is one of the biggest problems we have with our inability to pass electricity through those plates that are inside a salt cell, and then ultimately an inability to create chlorine. And that's simply because as that scale builds up, it's very sticky, it's very gritty, and it will adhere to those metal plates. And the whole point of the metal plates inside of the salt cell is that's what's conducting electricity back and forth through the water. Without the electricity, we don't break apart the salt molecule. If we don't break apart the salt molecule, we don't form chlorine gas, we don't form hypochlorous acid, and we don't sanitize the pool. So the electricity is kind of the catalyst to getting all that going. As scale builds up, then it's almost like an insulator, and you can't pass the electricity back and forth through those metal plates because they're coated with something that won't let electricity through. And then you can't sanitize the water. Now, inside that cell, because of the high pH, the higher the pH goes, the more hydroxide we have. The more hydroxide we have, the more scale we're able to form in the water. And that means we're more likely to build up calcium carbonate specifically on that cell, which is going to cause problems with us being able to generate sanitizer. Now, there's two common types of calcium-based scale that we find. Calcium carbonate is the sticky, gritty kind. Calcium phosphate also can cause problems with salt cells specifically. It's a little bit of a different type of scale. It's more fluffy, not nearly as sticky. They have different solubilities. I want to talk about calcium carbonate first because it's the culprit for a lot or most of the issues that we actually have in salt cells. As temperature goes up, calcium falls out of solution, right? So if you have a heater on your pool, that's why heaters get scale first and foremost before any other part of the pool. And also as water passes from the heater, the next stop in the system is usually your salt cell. So you've got hot water coming out of the heater inside that salt cell. Because of the heat, calcium is more likely to fall out of solution. Because of that, we're more likely to form scale. Add that to the fact that as your pH goes up, calcium's more likely to fall out of solution and form scale. And we've talked about why inside that salt cell, when we're leaving those hydroxide molecules behind, our pH is constantly going up, up, up. So it's hot, calcium's falling out. pH is high, calcium's falling out. Overall, just having a lot of calcium in the water is going to make calcium fall out. But ultimately, two of those three scenarios, temperature and pH, happen inside of that salt cell. And that means calcium carbonate scale forms very easily inside that cell and sticks to the metal plates. This is a picture I actually took in the middle of a field trial, and this was scale building up inside the cell. This had been after about 4 weeks in a cell, so it wasn't horrible, all things considered, but that's quite a bit of scale starting to build. And ultimately, it would have just kept piling up and piling up and piling up, and until we wouldn't have been able to move electricity between those metal plates. Now, calcium phosphate scale is very different. It's not driven by high pH, it's not driven by temperature, it's not part of that equilibrium. But what happens with calcium phosphate scale is it does not stay in the water. Once it forms, it falls out of solution very easily. It doesn't care what the parameters of the water are. Once you attach a calcium molecule and a phosphate molecule, you get this white flaky precipitate. A lot of times with saltwater pools, you see what I call snowflakes coming out of the return jets. And I know you guys have seen them when it spits out those white flakes out of the return jet. That is calcium phosphate scale. When you're seeing that, you have a phosphate issue. You have too much phosphate in the water. Your calcium's falling out of solution because of the pH and because of the temperature. But once that calcium falls out, then it's going to find phosphate if it's there, cause that scale. And then ultimately, you're going to end up with that white flaky mess that it'll come right out of the return jet, fall to the bottom of the pool and lay there. You can vacuum it up, but ultimately it's just going to keep forming. So I say if you have the snowflakes, you need to do a phosphate removal treatment to stop that from happening. Now, in some situations, calcium phosphate scale can actually contribute to the scaling of a cell. This is obviously a cell in terrible condition, but you can see on this cell 2 layers of scale. You can see the bright white scale that's underneath, and that's calcium carbonate scale. That formed first because that is the sticky, gritty, it's going to find those metal plates and hang on to them scale. Now, without calcium carbonate scale, calcium phosphate scale would have passed right through, come out the return jet, made snowflakes in your pool, and you would have had to deal with them in the pool itself. But because the calcium carbonate scale had laid down that barrier or laid down that layer on the actual cells, now the calcium phosphate scale is just piling on top. And it's making the scale worse and worse and worse. So the insulator is getting thicker and thicker and thicker, which means we're not passing electricity through. And this cell, we are probably not generating chlorine at this point at all. If we are, it's very, very little because the cell is struggling to move electricity through the water. This is a result of high pH, this is a result of high temperature, this is a result of not adding a scale inhibitor or something along those lines to help protect the cell. And also, salt cells have to be cleaned. They have to be cleaned periodically. They can't go years at a time and you not clean this off. You have to clean them periodically as needed. Most of them will tell you with a flashing light when they need to be cleaned, but ultimately that's not a step you want to skip because you can't make chlorine if you can't move electricity. And if you can't move electricity, it's usually because there's scale forming inside that actual cell. So there's things you can do, right? You can add scale inhibitors to keep calcium from being able to bond to carbonate or phosphate and keep that scale from forming. Now those are effective, but they're not 100% effective. So you are still going to get some scale buildup, but you can slow it way down by adding a scale inhibitor to the pool. You can reduce phosphate levels. That helps to get rid of the calcium phosphate scale or the snowflakes. Overall water balance, keep your pH in check so that calcium stays soluble in the water. Because if the calcium molecule itself stays soluble, neither type of scale is going to form simply because calcium is not available to form it. And then ultimately you can clean your cell regularly. But all of this, remember, we're talking about why can't we hold a chlorine residual in the water? And all of this is preventing that cell from ever being able to create chlorine. So one more quick look at a product. We do offer our Saltwater Magic Kit. It's a combination of two products. The first product is our Saltwater Magic Liquid, which is enzymes, which again help reduce the amount of waste that chlorine has to deal with, right? Enzymes clean up non-living organics, so chlorine doesn't have to. And a phosphate remover, all in one bottle. So we're reducing that calcium phosphate scale ability to form, and we're helping chlorine be more efficient in the water. And then ultimately, we have a Cell Protect, which is a stain and scale product that's put in there, focusing on protecting that cell from that scale buildup. Again, nothing protects a cell 100%, but it certainly helps slow down the process so that you clean less often and you have less issues with flow. Now, there are some water balance parameters that can lead to not enough chlorine. Low salt actually can be an issue. If you don't have enough salt, you can't break enough apart in order to create active chlorine. So you do have to make sure you have enough salt in there. But on the flip side of that, when you have too much salt in the water, electricity doesn't move as well as it should, and we end up not producing enough chlorine that way also. So you have to be careful, make sure you're maintaining it in the right range. And that varies a little bit from manufacturer to manufacturer, but make sure that you're just balancing appropriately. The other thing is low temperature. And low temperature is something that we overlook sometimes, but most cells don't activate or kick on until the water's between 65 and 70 degrees. Again, that changes a little from cell to cell, but when you open a pool in the spring and you flip that salt cell on, it's probably not generating any chlorine. So when you open, if that's what you're relying on to keep the pool clear, you're about to have a cloudy pool because you're not creating sanitizer. You're going to have to either hand feed chlorine for a little while, maybe put a couple of tabs in the water, whatever your options are, but you're going to have to feed a secondary source of chlorine until that water warms up to the point where the cell will actually kick on and start generating. And then finally, the cell life itself. You know, cells, they wear out. Those metal plates that we rely on to move electricity, they're coated with a metal called ruthenium, and that ruthenium is an important part of the process of moving that electricity through the water. That coating wears away, and as it wears away, we move electricity a little bit less, and ultimately, we get to the point where we're not moving enough electricity to sanitize the pool. That just means the cell's worn out and you have to replace it. So life is measured in hours. The more hours those metal plates are activated, the faster it's going to fail. So it's only got an infinite or a finite number of hours that it's going to operate. So if you're relying on something like the boost button to maybe oxidize the pool, try to catch up, try to overcome a chlorine demand, you're really shortening the life of the cell every time you do that, because the boost button kicks on the chlorine for 24 hours. Is that always true? Does it always kick on the chlorine for 24 solid hours? No, and that's again part of the problem when we're relying on the boost button is if you hit the boost button and 6 hours later your pump shuts off because it's on a timer, you didn't boost the pool for 24 hours, you boosted it for 6 hours. So you don't get nearly as much chlorine as you think you did. And also, if you're running every day at 70% for your dial setting and you hit the boost button, you don't go to 170%. You go to 100%. So you're only getting 30% more chlorine, but again, you're shortening the life of the cell. So people ask me, you know, can I use the boost button to troubleshoot cloudy water? Can I use the boost button to troubleshoot algae? So if I owned a salt pool, I'd never use the boost button. And that's just my opinion because it makes it really hard on the cell and you're shortening the life of the cell every time you do it. Again, it's okay to shock a saltwater pool. It's okay to add secondary chlorine in order to help you troubleshoot. Relying on the boost button it's a bit of a challenge to figure out exactly how much chlorine you're actually going to get out of it, and also is it enough to overcome the problem that you've got. Excessive combined chlorine, and we're rolling here to the end. I'm wrapping up so we can take some questions here. Excessive combined chlorine can be an issue in saltwater pools simply because we don't shock them. And a lot of times we don't even hit the boost button. We just let it roll along because you're constantly making chlorine, and that's great. But when you get a lot of bather waste, you get a lot of nitrogen that comes into the water, whether it's from fertilizer or source water or rainwater or whatever that is, and you're not oxidizing the pool on a weekly basis, which would be part of your maintenance routine for a traditional chlorine pool, you tend to see that those combined chlorine molecules build sometimes at a very rapid rate. So we recommend like shock the pool weekly. Use a non-chlorine shock if you want to. Non-chlorine shocks are great for breaking down chloramines. That would be a monopersulfate based shock, right? We have a pro series, it's called Shock Oxidizer. There's a lot of versions of it out there though. But non-chlorine oxidizer breaks apart that combined chlorine. It doesn't rely on your cell to do the work, so you're not shortening the life of your cell. It's easy to apply. If you already have plenty of chlorine in the water, you're not boosting that level back to the point where you don't want it to be, but you're able to break down that combined chlorine. And again, it can build very quickly because in traditional chlorine pools, we shock once a week, or you should shock once a week. And that is part of the process of taking care of combined chlorine. In salt pools, we overlook that. We don't do it. And so they can build up very quickly. Sorry, we talked about the boost button. I got ahead of myself. Apologies on that. But then the final piece I want to very quickly talk about, and then I'll take whatever questions that you have, is cloudy water in saltwater pools. And cloudy water, the problem with cloudy water is simple. You have to figure out why it's cloudy. And the first question you always have to ask is the water balanced? Yes or no? And if you say no, the water's not balanced, then your first look needs to be what's out of balance and how can I fix it? In a saltwater pool, most likely it's going to be pH that's out of balance. If you say, is your water balanced? Yes, the water's balanced. Why is my pool cloudy? Then you need to look at the physical causes of cloudy water. Physical causes are always centered around circulation and filtration. Inadequate filtration is the most common reason pools go cloudy. We take water samples into our labs over the course of the summer, and sometimes we get them from pool professionals that say, I've done everything I know to do and I can't clear this pool. Can you help me? Like, sure, we'll take a look at it. We have labs full of equipment that cost millions of dollars. And the first thing that we reach for to test cloudy water is this little piece of plastic that probably costs 20 bucks and a little piece of paper that simulates a sand filter. And we simply pour the water through the filter. And then we see how clear it is on the other side. 75% of all samples that come in that the professional can't get clear, 75% of them clear immediately just by filtering them properly. So that means you could throw all the chemicals in the world at it. You could bump your cell, boost your cell, turn it up as high as it can go. But if you haven't fixed your filtration issue, then you're not going to be able to clear that pool no matter what you do. So that's always the first place to look. And filtration, again, is linked to circulation. So look at your variable speed pumps, check the programming on them. Make sure that you're turning over enough times to really adequately filter and treat the water that's in that pool. Now, if the water's not balanced, right, you have to look at the impact of that. The big one, obviously, is pH. Higher pH causes things to fall out of solution, such as calcium. And as things fall out of solution, you can see them. And when you see them, you're seeing cloudy water. So the higher the pH goes, the cloudier the water is going to be. With that, if your alkalinity goes up, your pH tends to go up with it, causing cloudy water. If your calcium goes up, your calcium hardness level gets too high, and the water can't hold on to the calcium. It falls out of solution. We form scale. Scale ultimately contributes to cloudy water. So anything on the high side, total alkalinity, pH, calcium hardness, anything on the high side of the balance parameter that it's supposed to be at will ultimately lead or contribute to cloudy water. And then finally, the impact of sanitizer on cloudy water. If you don't have enough sanitizer, whether you're not making enough or you have a demand, once you don't have any sanitizer, bacteria grows, algae grows, and as you see it start to grow, water tends to start to become hazy. The hazier it gets, the more chlorine it's going to take, or algicide or whatever you're using to clear it, the more it's going to take to reestablish clear water and reestablish your sanitizer residual. Don't rely on your boost button to do that. Again, don't be afraid to shock the pool independently of your actual cell. You will find you get much better results much faster, and it's a lot easier on your equipment. So keys to clearing water. Salt pool, remember, is a chlorine pool. Use clarifiers, use flock products, balance your pH, make sure you have a sanitizer residual, shock the pool, pay attention to the filter, check your programming. All of these things you would do on any pool that turns cloudy, and that's kind of the point, is clearing a saltwater pool is no different than clearing any other pool, but you have to be willing to go outside of just relying on that cell to do all of the work for you. All right, so just suggestions for success: test often, balance the pH. Don't be afraid to add enhancers. It's not just salt. Borates make a big difference. Enzymes, phosphate removers, all of those products can make it a lot easier to maintain the proper water balance and also make it so that the cell can be dialed down, run less, and it will last longer. And then if something starts to go wrong, troubleshoot it early. Don't let it get to a full-blown problem before you're trying to fix it. The earlier you catch it and deal with it, the easier it's going to be to solve the problem. So again, our Saltwater Magic Kit is a great way to just help with overall maintenance and relieve some of the pressure on the cell, help it keep up a little bit and be able, again, to establish your chlorine residual, maintain your chlorine residual, and make sure that water stays clean and clear. So with that, Scott, I'll throw it to you to pull any questions we have out of the chat or take any questions we have. Just one thing, if you want any more information on any of the products I mentioned, you can scan this QR code right off your screen, and that will link you to our product catalog, and it'll give you information on all of the products that I mentioned. But Scott, what do we have for questions?
Oh, actually, we won't be able to get to all of them. I'll get to the ones we can. That was great stuff, Alicia. The anecdote about pouring a sample of water through a little paper filter and seeing it right there. I think that's a great tip for people. We do focus on chemistry in the pool, but as that illustrates so well, often, there's just so many filtration issues that we also need to keep in mind.
For sure. Yep.
Here's a question that takes us back to when you're talking about phosphate and calcium carbonate and so forth at the cell. It says, will a phosphate test show the presence of phosphates if they have already bonded with calcium and formed calcium phosphate scales? So you've got some already combining so now you're testing, which I just thought was an interesting question.
Yeah, that is an interesting question, and I'm going to say, and I've always said I'm never afraid to say I'm not sure, and I'm not sure. I can certainly find out, but I believe yes. I believe it still registers as an orthophosphate, and you could still test it, but I'm not 100% sure, and I don't ever want to mislead anybody. So I'd be happy if you can maybe grab contact information for that person. I'd be happy to follow up. I don't know for sure. That's a great question, and one I have never been asked before.
Hey, we have an award for that one. Do you recommend saltwater systems in spas?
Properly maintained spas, sure. The problem, well, not the problem, the challenge is spa chemistry already drives pH up because of hot water chemistry and carbon dioxide chemistry, and there's a slew of reasons why pH is driven up in spas. Adding salt and saltwater chemistry to that makes that, it compounds that challenge of maintaining pH. Ultimately, it's a great way to get a steady stream of sanitizer in the water. It's a great way to make sure that you're constantly killing bacteria and all of those things. But my biggest thing would be just absolutely make sure that you keep that pH in check, because 8.0, which sometimes people give up and say, oh, that's good enough. Remember, at 8.0, 25% of your chlorine is working and 75% of it isn't. So just keep those ratios in mind as you're balancing. You've got to keep that pH down.
Right. This question goes back to when you were talking about stabilizer and the effect of UV on your chlorine in the pool. And the question is, how do you deal with high CYA levels as you're trying to stabilize your pool?
I'd have to have a little more context, I think, to that question to give a full answer. Ultimately, we ask for a minimum. We want to, for a saltwater pool, 50 to 60 parts per million. As it gets beyond that, we don't really, we don't really care, for lack of a better way to put it. We don't see any impact from the higher levels of CYA causing issues with your, the chlorine that you're generating being able to work. So ultimately, we're more worried about you having enough and make sure that you have a minimum residual. But as it goes up, and that's honestly, Scott, that's a whole different presentation and a whole different discussion that we could spend an hour on alone. So I'm not trying to dodge the question at all. Ultimately, my answer is we don't really worry about high levels of CYA because we don't see an impact with them in the water. But again, something that maybe we can address on a webinar in the future and really dig into that question.
Okay, we got time for one more.
All right.
And I love this one. It may give you a little time to think on it, but what do you think is the biggest challenge to saltwater pools? The biggest challenge?
The biggest challenge to saltwater pools is naivete, or I want to say ignorance, but that sounds harsh. It's people not understanding saltwater pools. They're not hard to take care of if you do it correctly, but the biggest problem is that overwhelming perception of all you have to do is add salt. And if you rely on that, then you're going to have problems. Your equipment's going to fail, and you're ultimately going to have a bad experience. You may be okay for the first season, but then the problems are going to come in. So pH is a problem and scale can be a problem and all those things, but with that perception of all you have to do is add salt, which I think as an industry, we're doing a pretty good job of starting to overcome that perception that's out there. But I do think that's the biggest challenge, because once you understand how to take care of a salt pool and what has to be done, then ultimately it's great. It is automated and it is constant, and you are always feeding sanitizer and all those things that are important in pool chemistry, and you're not carrying active chlorine in your car or whatever. So it's great technology. It's just, that's the biggest thing. It's just a lack of knowledge about really what it takes to take care of them.
Got it. Brilliant stuff, Alicia. I want to thank you for coming. I learned so much today, and I value everything that I got out of this presentation. And I wanted to thank all of our huge audience for coming and sharing this hour with us. Learned a lot, but of course the day's not done, so we'll all get back to work. And
well, if anyone has any questions, my email is up on the screen. Feel free to reach out to me. I'm happy to take questions from that maybe I didn't get to or you didn't get a chance to ask. So I always like to interact.
And the webinar in its entirety will be made available for all the registered attendees, so you can review it at your leisure.
Perfect. Thank you, Scott.
Thanks, Alicia. Everybody take care. Bye-bye.